Hello and welcome to the fourth lecture of this short course called Behavioral Theory of Systems with a view towards data driven control. Up until the last lecture we saw that systems can be described through their behaviors, right? And the kind of systems that we are discussing, namely linear dynamical systems, shift invariant, described by either difference equations or differential equations with constant coefficients, mostly real coefficients. For such systems, the behaviors are given by kernel representations of polynomial matrices, where these polynomial matrices for continuous time systems are such that they are matrices with entries from the polynomial ring of size G cross Q, where we have Q number of variables of interest and G number of equations. And likewise, for the discrete time case, this is a matrix of LoRa polynomials with real coefficients. Okay? Before we move on, perhaps it would be nice to see yet another example of a behavioral description of systems like this. Okay? For that, let us consider this very nice electrical engineering example. This is that of a speaker. So how does a speaker work? Here is an electrical circuit. Okay. Here is an electrical circuit. Right? This is an electromagnet. Okay, this is the resistance of the coil. This together is the inductance of the coil, and here there sits a magnetic core, often called the bobbin also, which is attached to what is known as a diaphragm, which is a soft material which is connected to the frame of the speaker through a spring-like structure. What happens is, when there is a signal, when a signal comes in the form of a voltage, it produces a current. That current goes through the coil and sets up a magnetic field, and that magnetic field causes this core, which is a magnetic material, to move, right? And this movement causes this diaphragm also to move, which is attached to the spring. So there is a spring-like action. So this guy moves, this whole diaphragm moves, and that diaphragm, the movement of the diaphragm is the one that causes the sound wave, right? That's how a speaker works. If you have seen such speakers in your local neighborhood functions, those big speakers, sometimes their covers are open and you can see this diaphragm beating like that, like a heartbeat. Yeah. So that beat is what is caused by the movement of this bobbin, right? And those movements, the movement of the diaphragm is the one that causes the sound waves. Yeah. So this causes the sound waves and the music that we hear. So that's the speaker. Now, the question is, the idea is to convert this electrical signal, which is in the form of some music or speech or whatever, some electrical signal, and that signal needs to be produced faithfully at the output in the form of sound. Yeah. So how do we design the system? How do we control this system? First of all, we have to do the mathematical model of this system, and we'll see that we can write those mathematical model in the form of a differential equation, which can be written in the form of the kernel representation that we have seen. So to do that, what we will do is let me try and write down the equations here. So for the electrical circuit, we all know by applying KVL, we can write that V is equal to I times R plus L times di by dt. Okay? And then there is this current. So that current causes a force F on this bobbin, the core. The bobbin experiences a force which is directly proportional to this armature current, and as far as this force is concerned, this force causes this X to move. The bobbin has a mass m. So once again, following Newton's law, it follows that the mechanical part of this circuit satisfies the equation. There will be some oh sorry, I should not use this letter D, or rather perhaps I can use capital letters m d dx dt. This is due to some friction, assuming it's viscous friction is directly proportional to the velocity, plus some spring constant Ks times x that ought to be equal to the force, which is Km times I. I'm directly writing this equation so that I don't need this variable f anymore. So that is the equation that it satisfies. And is it all? Well, not exactly, because you see, because of the movement of this core within the coil, this is a magnetic material which is moving inside a coil. So it will set up what is known as a back EMF, right? Lenz's law of Faraday's law, it will set up a voltage in the reverse polarity so that it tries to force a current in this direction, which opposes the movement of the current, right. So therefore, there will be a plus, and it so happens that if you set your units properly, then it's the same, it's directly proportional to the velocity x dot, and the proportionality constant is the same Km. But that's not very important, it can be different also, doesn't really matter. So that's these are the two equations that we have, equation number 1 and equation number 2, right. How can we write this down in the form of that we have been seeing so far? Well, let me rewrite these two equations in the next page. We have V minus R I minus L di by dt minus Km dx by dt, that is equal to 0. That's my equation number 1. It's a rewritten form of equation 1. And we have the other mechanical equation, which looks like m d square x dt square plus d dx dt plus ks times x minus Km times I equal to 0. That's my equation number 2. So my variables are V, I, and x. Okay. In order to write down the matrix, I will just write this equation down in the form of a matrix now. 1, then minus R plus L xi, xi stands for ddt, remember, minus Km times xi. Okay, that's the first equation. and the second equation is minus km here, 0 here, and m xi squared plus d xi plus ks. That is the equation. So, this is my polynomial matrix R xi. In this case, the size of this matrix is 2 cross 3, right. So, then this Vix, these are my behavioral equations, kernel representation equations. Okay. All right. So, I hope you see the kind of system, the meaning of this equation that we have been writing. Yeah, without bothering to write down transfer functions and or state space representations. This is the, okay, sorry, I missed one point. This is equal to 0. Yeah. So, this is the fundamental form that we have introduced in this type of description of dynamical systems, right. Now, moving on, the question that we are going to ask here is that in today's lecture is that what if we have multiple equations? Yeah, what if we have multiple equations describing, can different equations describe the same behavior? That is the question that we are trying to ask, right. Formulated differently, alternatively, if we have two sets of equations, can we verify whether these two sets of equations will give rise to the same solution set, rather in other words same behavior? Okay. So, to start with, perhaps it would be nicer to start with an example, of a differential equation, a system of differential equations. Now, an important point to note here is that in this course, at least in the initial part, we will be interested mostly in differential equations and not difference equations. Yeah, but similar ideas hold for difference equations as well, and this will become clearer as you solve the exercise problems that I am going to supply. Those exercise problems will have problems defined over difference equations, and if you solve those problems carefully, you will see that similar ideas hold for difference equations, I mean discrete systems, yeah, as the ones that are there for differential equation system, namely continuous systems. All right. So, this example, okay, example of a system of differential equations, right. I am sure that you have seen equations like this, d squared. So, let me not use this d dt again and again. Now that we have the Greek letter xi at our disposal, we should use it to the full extent. Suppose we have xi squared plus 3 xi plus 2, okay, that acting on w equal to 0. W is now just a single C infinity function, right. It is a single standalone differential equation, and you know how to solve this, right. All you have to do is you have to factorize this, and we all know that the factorization of this guy is xi plus 1 and xi plus 2, right. I think I have not made any mistakes here. Xi squared, xi and 2 xi and 2, yeah, this is okay. So, you factorize this, and then once you factorize, we know that the solution is given by, so this implies that the solution W is given by k 1 e to the power minus t coming from this root, and k 2 times e to the power minus 2t, that is coming from this root. Okay. Yeah, I hope you know about this, and that's, if you don't, then just brush up your knowledge of differential equations from your basic maths, engineering maths books. Okay. Now, what if we have another equation, right, For example, what if we have, let us say, xi squared plus, let me think, let us say 4 xi plus 3. I am sure you can understand where it is going. This is my equation number 1 and this is my equation number 2. I am going to solve this now. If you factorize this, if I am not mistaken, the factorization should come out to be xi 1 into xi plus 3, right? Indeed, yes, I think it is okay. And this implies that my solution W is given by, let me use k3 e to the power minus t plus k4 e to the power minus 3t. Okay. Now, so far so good. Two standalone differential equations, and we have their solutions at our disposal. What if I now pose this question, that what if I have a system of differential equations, two differential equations acting on the same variable that looks like xi squared plus 3 xi plus 2 and xi squared plus 4 xi plus 3. Both these equations must be satisfied by the variable w, right. In that case, how do I get the solutions? Now, you see, if I call B1 to be the behavior given by the kernel of xi squared plus 3 xi plus 2 and B2 to be the kernel of xi squared plus 4 xi plus 3, in that case the behavior given by the kernel of this matrix, if I define the behavior of this to be kernel of xi squared plus 3 xi plus 2 and xi squared plus 4 xi plus 3, if I do this, then just do a little bit of thinking and convince yourselves that I can write B to be equal to B1 intersection B2, right? Because something that is in the kernel of both these operators means that it must be in the kernel of this one, so it's in B1, and it must also be in the kernel of this this second polynomial, so it must be in B2, right? And vice versa. If something is in this intersection, then certainly it satisfies both these equations, so it's going to be in B. Very simple. But the question is, how do I get this intersection? Remember, B1 is given by, so I'm going to use a little sophisticated language, but if you don't feel comfortable, just bear with us. It will become, you will eventually get used to it. Yeah? B1 is nothing but the linear span of these two functions, e to the power minus t, e to the power minus 2t, right. On the other hand, B2 is the linear span of e to the power minus t and e to the power minus 3t, if I am not mistaken. Let me just check whether everything is correct. Yeah, this is the linear combination, this is the linear combination, right. If you don't remember, k1, k2 must belong to real numbers, k3, k4 must also belong to real numbers. Okay. So, these are the basis vectors for B1 and these are the basis vectors for B2. That is why B1 is the span of e to the minus t, e to the minus 2t, and B2 is span of e to the minus t and e to the minus 3t. So, what can be there in the intersection, right? Having something in the intersection means that we should be able to find out constants a, b, c, d such that a times e to the power minus t plus b times e to the power minus 2t is equal to c times e to the power minus t plus d times e to the power minus 3t, right. Taking all of them on one side, this means a minus c e to the power minus t plus b e to the power minus 2t minus d e to the power minus 3t must be equal to 0. Now, this goes to you as an exercise. show that e to the power minus t, e to the power minus 2t, e to the power minus 3t, these three functions are linearly independent, right? If you have done a course on linear algebra, you know the meaning of this. That means no linear combination, no non-trivial linear combination of these three functions can give us the zero function. Zero function is a function that is identically zero for all time. Yeah, they must be linearly independent. These functions must be linearly independent. It's very easy to check. Just use some derivatives and then use van der Monde matrix kind of ideas. But you can show that these matrices, as long as these these exponents are different, the functions are linearly independent. Now, if these functions are linearly independent and I have a linear combination which goes to 0, this is the 0 function, right? It is 0 all along. I want this to be 0 all along for all time, because these two functions are equal for all time, right? So this has to be for this to be identically 0, and because these guys are linearly independent via the exercise, it means that these coefficients must all be 0. So a minus c must be equal to 0, b must be equal to 0, and d must also be equal to 0, which then means that we have only one possibility, that a is equal to c. So that means if there is something in the intersection, then that must be of this form. So the intersection, that is the behavior B, must then be the span of e to the power minus t, you see, because anything that is in the intersection must be of the form a e to the power minus t. Okay, so this is the intersection. But you see, if this is the span, we already know a differential equation which gives us this behavior, right? What is that? You see, d dt plus 1 acting on w equal to 0, that is kernel of xi plus 1, in that case is equal to b, you see. So what have we seen here? We have seen here that on the one hand we have the kernel of these two polynomial matrices, these two polynomials, so this polynomial matrix, and then we have the kernel of just xi plus 1, and it turns out that the two behaviors are equal, right? So if somebody gives me a system of equations which is this, and a single equation which is this, yeah, that is xi plus 1 w equal to 0, these two different systems of equations actually give rise to the same behavior, right? So when does that happen? When we have two different sets of equations give rise to the same behavior. This was a very simple example which was very easy for us to work out, but what will happen in the general case? Think about it. Suppose I have a polynomial matrix R xi, okay? Right? And then suppose I am looking at this behavior which is given by kernel of R xi, okay? Now, suppose I just take some other polynomial matrix f xi, which is of size say R g prime. I'm sometimes will write the powers like immediately after R and then put the xi, and sometimes I will write, so this is a disclaimer, remember that when I write R g cross q xi and I write R xi g cross q, the two are the same. There's a subtle difference between the two, but let's not worry about that at this point. Yeah, these two will mean the same thing for us. Okay, so suppose I take a matrix like this and then I create an R prime xi defined as f xi times R psi, okay? Now here's the claim. Suppose I define B prime with this I define B prime to be equal to kernel of R prime psi. What can you say about the relation between B prime and B? The claim is that B will always be contained in B prime. Any trajectory in B must automatically be there in B prime because B prime has been defined like this. What is the reason for that? It's very simple, in fact. Think about it. Suppose I take a W in B. That implies R psi times W must be equal to 0. That obviously implies that no matter what F is, F psi times R psi times W must also be 0 because this is already 0, and when any polynomial matrix acts on a 0 function, it certainly produces 0, right? You take the 0 function, make any difference, whatever differentiation you do of the 0 function, you get 0 again. So any polynomial matrix acting on 0 function produces 0. So this is equal to 0. This means R prime psi W equal to 0, which means W is an element of B prime. You see, B is contained in B prime. Okay? Now, this is very good. What if we look at the special situation where, where this F matrix is square? So, okay, suppose I have R psi like before. I have R psi, which is a polynomial matrix of size G cross Q. Okay, and now I have an F psi, which is a square matrix G cross G psi. Okay, and it produces, and I produce this R prime psi, which is F psi acting on R psi. Because F is a square matrix, the size of R prime and R are the same. This also is a G cross Q matrix. Okay. So obviously now if I define B to be the kernel of R psi and B prime to be the kernel of R prime psi, then as we have seen before, B prime contains B. Okay? Now what if F psi were invertible? F psi invertible. Now we have to be very careful about this inverse. What do we mean by invertibility? Once I take this inverse, if R is invertible, then R psi must be equal to F inverse psi R prime psi, and in that case I can just reverse my logic and say that B now contains B prime. So both the containments are there, so my B prime must be equal to B. But what do I mean by invertible? You see, that invertibility should mean that, you see, it should be like this, yeah, like this product, which necessitates that F inverse must itself be a polynomial matrix. Now herein lies the problem. Herein lies the fun also. Given a polynomial matrix which is square, F psi, how do you get its inverse when it's a square matrix? The same formula. Look at F, find out all its cofactors, write this adjugate matrix, adjugate of F, which of course is also a polynomial matrix because in the cofactors are just multiplications and additions. So multiplication of two polynomials is a polynomial, addition of two polynomials is a polynomial. So this is a polynomial matrix, but now wait, you have to divide by the determinant of this matrix. And now when you divide by the determinant, yeah, if the determinant is a polynomial, then the entries of this whole product are not polynomials but rather rational functions. This is a rational function matrix in general, G cross G, rational function matrix. Great, no? But I want polynomial matrix. When can I get polynomial matrix? That is a polynomial matrix if and only if determinant of f psi is a non-zero constant. That means it belongs to the set of real numbers sans 0. Okay? Such matrices are called unimodular matrices. Right? Yeah? So that way we have our first non-trivial result. We have a sufficient condition for two systems of equations giving rise to the same behavior. If we have a polynomial matrix R psi, another polynomial matrix R prime psi, both are same size, and the two are related like this, that R prime psi is equal to U psi R psi, where this guy is unimodular. Yeah, then this implies kernel of R psi is equal to kernel of R prime psi. Okay? What is the deeper meaning of this? It turns out that there is indeed a deeper meaning through module theory. That and much more is what we'll learn in the next few lectures. Yeah, see you then. Bye. Take care.